Going to review some items on polynomial functions and their graphs, starting with turning points. The graph of a polynomial function of degree n, where n is greater than or equal to 1, has at most n minus 1 turning points. So we'll have at most that degree minus 1, that number of turning points. The graph of a polynomial function of odd degree has an even number of turning points, or it could have none at all. Think about linear functions. They have no turning points, and those are odd degree functions. The graph of a polynomial function of even degree has an odd number of turning points. Think about parabolas, quadratic equations. Those are U-shaped graphs. They have one turning point. For zeros, for x-intercepts, odd degree functions will always have an odd number of real zeros. Again, think about linear functions. Those are odd degree functions. They have one x-intercept. Even degree functions will always have an even number of real zeros or no real zeros at all. Relate that to parabolas, quadratic functions, U-shaped graphs. If the graph crosses through the x-axis, there are two real zeros, two x-intercepts. If the graph hovers above or below the x-axis, there will be no x-intercepts. Now you might question that and say, what about a parabola that just touches the x-axis, where the vertex is sitting right on the x-axis? That's one x-intercept. Well, that gets into multiplicities, which we're going to talk about later in this video. For the end behavior, if the leading coefficient is positive and the degree is even, relate that to parabolas, quadratic functions. Where the coefficient of x squared is positive, it's an even degree function. If you have the coefficient of x squared being positive on a quadratic function, that parabola is going to open upwards. It's going to be up on the left and up on the right for the end behavior, up and up. If the leading coefficient is positive and the degree is odd, relate that to linear functions, where you have a positive slope. If you have a positive slope, that line's going to go up and to the right, where the end behavior would be down on the left side and up on the right side. So the end behavior would be down and up. If the leading coefficient is negative and the degree is even, again, relate that to quadratic equations or parabolas, where the coefficient of x squared is negative. That parabola would open down. That means it'd be down on the left side and down on the right side. So the end behavior would be down and down. And finally, if the leading coefficient is negative and the degree is odd, think about linear functions where you have a negative slope. That line goes down and to the right. It's up on the left side and down on the right side. So the end behavior would be up and down. We're going to see all those things hold true as we look at these graphs. For f of x equals 2x plus 3, starting with the end behavior. Leading coefficient is positive, the degree is odd, it's down on the left side and up on the right side. As far as the x-intercepts go, that is an odd degree function, has just one x-intercept. And for the turning points, the graph of polynomial function of odd degree has an even number of turning points, or I said it could have none at all, and that's the case here. This has no turning points. For f of x equals negative x squared plus x plus 5, the leading coefficient is negative, the degree is even. As far as the end behavior goes, it's down on the left side and down on the right side. As far as the x-intercepts, or the zeros, that is an even degree function and has two x-intercepts. And as far as the turning point goes, that is an even degree function. It has an odd number of turning points. It has one turning point. For f of x equals 2x to the third, as far as the end behavior, relate that back to a linear function. Where the leading coefficient is positive, the degree is odd, it's going to be down on the left and up on the right. So you see those two graphs have the same end behavior because the leading coefficients are positive and the degrees on both of those are odd, down on the left and up on the right. As far as the x-intercepts go on that is an odd degree function. It has one x-intercept. And the turning points, if you look closely here, you might think there are turning points, but there are none. Odd degree functions will have an even number of turning points, or it could have none at all. For f of x equals x to the fourth minus 3x squared plus 6x, as far as the end behavior, relate that to a quadratic. Even degree functions, quadratic functions, parabolas. If the leading coefficient is positive, the parabola opens upward. So it'll be up on the left and up on the right. And that's the same case here. Up on the left side, up on the right side is the end behavior. As far as the x-intercepts, you can see that there are two x-intercepts. That is an even degree function with two x-intercepts, or an even number of real zeros. And the turning points, there is just one turning point on this. This is an even degree function. It should have an odd number of turning points. There is just one turning point. That is not a turning point. That we're looking at right there, that is not a turning point. A turning point is where the y values completely reverse and go in the other direction. So be careful when you're picking out the turning points. there is just one turning point on that one. For f of x equals x to the fourth minus x to the third minus 4x squared plus x, the leading coefficient is positive, the degree is even. Relate that to a quadratic equation where the coefficient of x squared would be positive. It's up on the left, up on the right. That's the end behavior on this. Up on the left side, up on the right side. As far as the x-intercepts go, it looks like there are 1, 2, and 3 x-intercepts. So even degree functions will always have an even number of real zeros, but I just counted 3 x-intercepts. Well, the problem with that is you'd have to zoom in on that and see there are actually 4 x-intercepts. There are 4 zeros. So sometimes with the graphing calculator, you have to use a zoom or trace feature in order to see all the details. There are 4 x-intercepts there. Turning points. There are 1, 2, and 3 turning points on that. Even degree function, which will have an odd number of turning points, that particular graph has 3 turning points. Finally, f of x equals x squared plus 3, simple parabola. The leading coefficient is positive, the degree is even. That parabola opens upward. It's up on the left side and up on the right side, so the end behavior is up and up. As far as the x-intercepts go, that parabola has no x-intercepts, no real zeros. There would actually be 2 imaginary solutions there if you solve that for x. So even degree functions will always have an even number of real zeros, or in this case, no real zeros at all. That parabola does not hit the x-axis. And as far as the turning points go, a parabola will always have just 1 turning point. Even degree functions have an odd number of turning points. So you see all those things that we talked about up here hold true with these graphs, but sometimes you have to zoom in a little bit to see all the details. Some graphing calculators offer a coordinate chart to look at. You can pick things out from a coordinate chart. For example, turning points. The turning points will occur near where the value of y changes direction. So if you look at the values of y going 0, 28, 36, they're increasing, and then they start decreasing from 36 down to 30. So there should be a turning point on the graph near, doesn't mean it's dead on, but near the coordinates negative 3, 36. So if we go to the left 3 and up 36, you can see there is a turning point near those coordinates. Another turning point, if you watch the y values, they are now decreasing from 0, negative 12, negative 14, but then they start increasing from negative 14 to 0. The y values are changing direction near the coordinates of 2, negative 14. So if we go to the right 2 and down 14, you can see there is a turning point near those coordinates. Again, it does not mean it's dead on at 2, negative 14, but there is a turning point very near those coordinates. Also, you can pick out zeros or x-intercepts. At x-intercepts, where the graph hits the x-axis, the value of y is 0. So if you look at the coordinate chart and look for where y is equal to 0, those are the x-intercepts. So 3, 0, 0, 0, and negative 5, 0, that graph is hitting the x-axis at 3, at 0, and at negative 5. Those are the x-intercepts, so you can pick things out from a coordinate chart, turning points, x-intercepts, and you can also see those obviously on the graph. Multiplicity of 0, or you might think of this as multiplicity of x-intercepts. What we're going to look at is what the graph looks like when you get x equals something more than once. So let's say you're solving an equation and you get x equals 2 and x equals 2 again. That's going to give that graph a certain appearance where that x equals 2. Different from if x equals 2 just one time. So that's called multiplicity. If you get x equals 2 again, and x equals 2 again. If you have x equals 2 3 times, that would be a multiplicity of 3. If you get x equals 2 one time, that's a multiplicity of 1. And each of those multiplicities gives that graph a certain appearance at that x-intercept. If a is a 0 of multiplicity n, so if a is an x-intercept, or x equals a n times, in a polynomial function, then the behavior of the graph at the x-intercept a will be this, close to linear, if n equals 1. So if you get x equals a one time, then that graph will look like a straight line where that x equals a, where that x-intercept is. If the multiplicity is 2, so if you get an x-intercept that shows up 2 times, then that graph will look close to quadratic or take on a U shape at that x-intercept. If the multiplicity is 3, if you get x equals something 3 times, then the graph will look close to cubic at that x-intercept. It'll take on an S shape at that particular x-intercept. You see it better when we actually look at a graph and an equation such as this. F of x equals x to the fourth minus 2x to the third minus 8x squared. That is the graph of that equation. Now if we go to solve that for x algebraically, look for a common factor that you could factor out. X squared would be a common factor to those three terms. So if you divide each term by x squared, you get x squared minus 2x minus 8 in parentheses. Now that will factor into two binomials. That x squared minus 2x minus 8 factors into x minus 4 times x plus 2. So we have x squared times x minus 4 times x plus 2. That equals 0. All three of those equal 0. But keep in mind, and this is the catch that you're going to see on that graph, x squared is really x times x. So x is going to equal 0 twice. Because if x squared equals 0, then x equals 0, and x equals 0 again. So set all three of those equal to 0. X squared equals 0, x minus 4 equals 0, or x plus 2 equals 0. Solve each one of those for x, you get x equals 0, but keep in mind, the multiplicity there is 2. You get x equals 0 two times. So x equals 0 twice, x equals 4, and then x equals negative 2. So looking at the multiplicities, 0, where x equals 0, that has a multiplicity of 2, because it was x times x. So x equals 0 and x equals 0 again, that is a multiplicity of 2. And remember, the graph will look close to quadratic where x equals 0. So if we look at that graph where x equals 0, you can see it takes on a U shape where x is equal to 0 because that multiplicity is 2. X equals 4. Now that only showed up once in our solutions. X equals 4 just one time. And if you look at that graph, it looks somewhat like a straight line going through 4 on the x-axis. So it takes on a linear appearance when the multiplicity is 1. And then finally, for x equals negative 2, we just got that once. So x equals negative 2 just one time. The multiplicity is 1. The graph should look close to linear where x equals negative 2. And you can see just for a short segment there where the x-intercept is negative 2, it does take on a linear appearance. So you can see if the multiplicity is 2, there is a U shape to that graph where x equals 0. If the multiplicity is 1, such as where x equals 4, there's a linear shape to that graph where x equals 4. And the multiplicity on x equals negative 2, the multiplicity on that was 1. And it does, again, take on a linear shape where x equals negative 2. We're going to find the zeros, the multiplicities, and describe the behavior at these zeros. F of x equals x to the third minus 4x squared plus 4x. That is the graph of that function. We're going to solve this algebraically. Look for a common factor that you could factor out. X is a common factor of those three terms. So we set f of x equal to 0. We're finding the value of x when y is equal to 0. In other words, we're finding the x-intercepts. So once again, factoring x out, you have x squared minus 4x plus 4 in parentheses. Factor that into two binomials. That will factor into x minus 2 times x minus 2. So we have x times x minus 2 times x minus 2 equals 0. All three of those multiply together to equal 0. So that means all three of those could be equal to 0. X could be 0, x minus 2 could be 0, or since we're talking about multiplicities now, x minus 2 could be 0 again. So you get x equals 0, x equals 2, and x equals 2 again. So that 0, where x equals 0, that has a multiplicity of 1. In other words, it shows up once in our list of solutions. With that being the case, with that 0 being a 0 or an x-intercept with a multiplicity of 1, the graph will appear close to linear where x equals 0. And if you look at that, just for a short segment there, it looks like a straight line crossing through 0 on the x-axis because the multiplicity of that is 1. It just shows up once in our list of solutions. But for x equals 2, that has a multiplicity of 2. In other words, it shows up twice in our list of solutions. So 2 would be called a 0 or an x-intercept of multiplicity 2. In other words, it just shows up twice in the solutions. Now, with that being the case, since the multiplicity is 2, where x equals 2, the graph appears quadratic, or looks somewhat like a parabola where x equals 2. Looks like a U shape going through 2 on the x-axis. So when the multiplicity is 1, the graph will appear close to linear, look like a straight line when the multiplicity is 1, or when the solution just shows up once. But when the multiplicity is 2, x equals 2 two times here, the graph will appear close to quadratic or look like a mini parabola where x equals 2.